In this video, we're going to discuss one of the trickier concepts in probability, and that is called conditional probability. Now, you're going to see this kind of weird notation. Previously, we had, capital P parentheses E is the probability that the event E is going to happen. Now we have this weird slash, and then we have two separate events. Does this mean like E and F, E or F? It doesn't mean actually either of those. What this means is this is the probability that E will happen, and then we say given F. Of course, what does that even mean? So that means we somehow know the event F is going to be true. What is the chance that E will happen? So the idea is when we have this conditional probability, this given F here, we're saying we happen to live in a universe where it's guaranteed that the F event is going to happen. It's going to be true. So in that universe, what is the probability of E going to be? And the way that we generally calculate this is the probability of E given F is the probability of E and F both happening divided by the probability of F. And so if you're ever asked to calculate a conditional probability, you will use that formula to do so. You'll somehow find the probability E and F. Maybe it's given to you in the problem, maybe not. You will then divide it by the probability of F, and that will give you the conditional probability. Okay. Now, another way of thinking about this is the idea of independence that we saw in the previous video. So what does independence mean? It means that whether one of them happens doesn't affect whether the other one's going to happen. So in other words, that means the probability of E, if we know that F is going to happen, is going to be the same as just E normally. So the fact that we know F is guaranteed to happen is not going to affect the probability that E happens. So independence means that the conditional probability is the same as the normal probability. It doesn't actually get changed there. That's another way you can kind of try to figure out whether you have two events are independent or not. Look at the conditional probability versus the regular probability. If they're the same, it's independent. If they are different, it is not independent. Now, a lot of times in problems, they will just give you the conditional probability. They won't ask you to calculate. They will give you the conditional probability, and then you will use that to then solve something else. And in particular, we're going to have the general multiplication rule now. So in the previous video, we had the multiplication rule that only worked when you had independent events. This one will work always. It says the probability of two events E and F happening is the same as the probability of E given F times the probability of F. Now really, if you look closely, this is just the exact same as the formula I already gave you to calculate the conditional probability, but just multiplying both sides by P of F. And in my experience, I use this top version more often in solving problems than the bottom version down here, because a lot of the times you are trying to find the conditional probability, whereas to use the bottom formula, you already have to know the conditional probability. Now, sometimes you will do it that way and it's fine. Here's an example of a conditional probability that you could find and then use this formula here. Let's suppose a bag contains 3 blue balls and 4 red balls. You pull one ball out, set aside, and write down the color. then pull a second ball out. So what if I wanted to ask you, find the probability that the second ball is red, given that the first ball is blue? So we're saying that we are going to be in a situation where we know the first ball was going to be blue that got pulled out, and then we're looking at what is the chance of the second ball being red. Well, originally there were 3 blue balls and 4 red balls. And we are saying the given part here, the thing that we know, is that the first time we grab out, one of the blue balls is going to be taken out. That means after we pull the first ball out, there are 2 blue left and 4 red left. So now, what's the chance in this scenario that we're going to get a red? Well, there are 4 red left out of 6 total left. So the probability that the second ball is red, if we know the first ball is blue, is 2/3. On the other hand, if I had said find the probability that the second ball is red, given that the first ball is red, we're going to get a different answer here. We still start with 3 blue and 4 red, but now I know that the first ball is going to be red. So that means that after I've done that, there are 3 blue and 3 red left. So that means there are 3 red that might happen in the second pull out of 6 total balls remaining. So this one has a only 50% chance of being red. So you see, depending on whether the first ball was blue or first ball was red, it changes the probability here. That means they're not going to be independent events. Anyways, so sometimes you can just look at a problem and try to figure out what this conditional probability is, but more often you would use this formula up here to calculate a conditional probability. It's somewhat rare that we'd actually use the second rule here, but you might, for example, going back to the pulling the balls out of the bag, let's suppose I want to find the probability that the first ball is blue and the second ball is red. Well, you would use this general multiplication rule to work out the answer there. Now, with that said, there are a ton more we could talk about with conditional probability. But in this class, we don't go too deep into it. It's just not one of our main focuses. And you definitely want to get down the basics here. There's one more thing I want to mention in this video, though, and that is the difference between P of E given F and P of F given E. So E given F means we know F happens. Find probability of E. And the probability of F given E here would be we know E happens. Find probability of F. And in general, these two numbers are going to be completely and totally different. In fact, one of them could be a really high probability, one of them could be a really low probability. To give a real-world example, since we're still dealing with the pandemic here, let's suppose the event E is you have COVID, and F is you test positive for COVID. And you might say, well, these are the same thing, and they're really not, because tests are not perfect. So when we say the probability of E given F, this is the probability you actually have COVID if the test is positive. On the other hand, the probability of F given E is the probability the test is positive if you actually have COVID. And it turns out, something we're going to learn much later in this class, is that these two probabilities are in, at least not exactly, but somewhat of an inverse relationship. in that when they are designing the COVID test, they can make one of these really small or large, but the other one's going to get the reciprocal nature of it. So for example, if you make one of these really high chance, the other one's going to be really low chance. And that's what happens when they're designing these tests. A lot of times in a case of something like this, they would worry more about this second probability here because they want to make sure that if you actually have COVID, the test says you have COVID. Because if the test was wrong in that case and you actually have COVID, then you're going to have COVID and you're going to be going out among people thinking you don't have it. You then might spread it and cause it to be worse. On the other hand, if the probability of E given F, if this one was larger, that just means the test says you have COVID when you really don't. And that can definitely be an inconvenience if you're quarantining when you otherwise wouldn't have had to. But it's better for people to quarantine when they don't have to than for someone who has COVID to be going out thinking they don't need to quarantine. So when they're designing these tests, they can try to make one of these a better probability, one of them, but the other one ends up becoming a worse one. And for each time they're making a test, they have to balance out which one they want here, which one they want to be more important. And like I said, for right now, that's a very vague idea. Why are these happening here? But we will get to it much later in the course, why these two things are kind of different from each other. Right now, though, we're just trying to get the idea of what is conditional probability and how do we do basic calculations using it.